Swayam Prabha. Digital India. Educated India.
Welcome to the 7th week of the open course on diffusion in multi-component solids. This is the 28th lecture in the series. In this lecture, I have talked about energetics of formation of vacancies and divacancies. Although I have not talked about other point defects such as interstitials and impurity atoms, similar treatment can be extended to the other point defects too. So, point defects play important role in governing the phenomena of diffusion. Vacancy is probably the most important point defect in the study of diffusion because it acts as a vehicle for diffusion. Vacancies mediate the atomic jumps and hence guide the diffusion. In this class, we will discuss the energetics of vacancy formation. Similar treatment can be applied to other point defects including interstitials and impurity atoms. So, to start with, what is a vacancy? A vacancy is just a vacant atomic site in a crystal, or it is a regular atomic site with the atom missing from the site. Now, it is easy to see that formation of a vacancy leads to increase in configurational entropy. So, for example, if we consider this two-dimensional lattice in which atoms are arranged periodically. Now, if we have to arrange n identical atoms on n atomic sites, we know there is only one possible way because all the atoms are identical. Now, instead of n atoms, let us say we have to arrange n minus 1 atoms and one vacancy on the n sides. So, let us denote the vacancy by a square. Now, obviously, there are n different ways in which the vacancy can be placed on n number of sites. And so, formation of a vacancy leads to increase in configurational entropy, and because of this entropic reason, vacancy is a stable point defect. Now, there is an increase in entropy, but at the same time you can see to form a vacancy the atomic bonds have to be broken. That means, there is also an increase in enthalpy, and so there has to be certain equilibrium concentration of vacancies at any given temperature and pressure, and this equilibrium concentration is achieved as a compromise between increase in entropy and increase in enthalpy because of the formation of the vacancies. So, in general, if we denote the Gibbs free energy of formation of vacancy, or more particularly let us call it a mono vacancy because we are considering only one vacancy at a time for now. So, it denoted as delta G 1 V. 1 V denotes the Gibbs free energy of formation of mono vacancy. It can be given as delta H 1 V minus T delta S 1 V. Now, this delta S 1 V term includes two entropy terms. One is obviously the configurational entropy let us call it delta S1V configurational, and the other one is the vibrational entropy. Let us call it delta S1B vibrational. Now, we can understand the configurational entropy. About the vibrational entropy, since the atom is missing from vacancy site, the neighboring atoms experience change in the mode of vibrations, and it leads to a positive change in vibrational entropy. So, in general, if there are n vacancies in the lattice, we can write delta Ag1V prime. The prime denotes that the total change in Gibbs free energy due to formation of n vacancies, the small n number of vacancies, can be written as n times delta H1V minus T n times delta S1V vibrational minus T times delta S1V configurational. It is easy to see that the enthalpy change per vacancy and the vibrational entropy change per vacancy are independent of the number of vacancies. So, for n vacancies we will multiply by number n, but the quantity delta S1V configurational, it depends on the number of vacancies. So, we need to express this delta S1V configurational in terms of the number of vacancies n. So, how do we go about finding the equilibrium vacancy concentration? So, we need to carefully create the vacancy thermodynamically in order to study the energetics of it. So, when I create the vacancy thermodynamically, it has to be a reversible process and the mass has to be conserved. So, what we do in order to create a vacancy, let us consider this crystal, and each atom is denoted by this cubic box here. So, we have to remove one atom from the interior, and we cannot just let it evaporate, because then there will be loss of mass. So, what we do, we place it back on the surface. Now, when we place it back on the surface, the number of open bonds on the surface should not change. So, the ideal location for placing the atom back onto the surface is at a surface step edge, like the one shown here. If we place this atom back on the surface at a surface step edge, we can see it will conserve the number of open bonds on the surface. So, we are conserving mass as well as number of open bonds on the surface. So, this is how we should create the vacancy in order to study its energetics. So, to create the vacancy, we are removing one atom from the interior, which means we are breaking Z number of bonds. Z here is the coordination number, and when we place it back on the surface, roughly half of the bonds are recovered. So, it seems that the enthalpy of vacancy formation should be about half of the enthalpy of sublimation. However, this is not true. Let us consider a couple of examples. First one is platinum. Delta S sublimation for platinum is about 5.6 electron volt. So, half delta H sublimation is about 2.8 electron volt, but delta H1V, the enthalpy of formation of a mono vacancy for platinum, is 1.51 electron volts. Similarly, if we consider copper, the sublimation enthalpy is about 3.33 electron volt. So, half of it is about 1.66 electron volts, but the experimentally determined value for delta H1V for copper is about 1.28 electron volts. So, we can see that delta H1V is actually less than half the enthalpy of sublimation, and the reason is when we form a vacancy, there is a electronic and elastic rearrangement that the crystal experiences in the region surrounding the vacant site. Now, when we remove an atom from its regular site, the adjacent atoms tend to fall into that vacant site. So, the effective volume of a vacant site is not same as the effective volume of an atom in an otherwise perfect crystal. Similarly, the electronic charge density changes because of the removal of an atom from the metal, and so there will be electronic rearrangement in order to maintain the charge neutrality, and because of that the enthalpy of mono vacancy formation is actually less than half the enthalpy of sublimation. Swayam has discussed a nice model for this. He considered the mono vacancy formation in copper and he split the process in 6 different steps. In a metal ions are held together at their regular lattice positions by the cloud of electrons, right. So, the first step he considered was sublimation of one copper ion from the interior. So, he denoted this as Cu plus from solid and the interior of the solid to Cu plus in gas state to infinity. And once the copper ion is removed, to maintain the charge neutrality we need to remove one electron. So, the second step is sublimation of one electron from the interior. So, electron from this interior of the solid to electron to gaseous infinity. Then combining the electron with copper ion. So, copper ion at infinity plus electron infinity gives a copper atom at infinity, and then putting that copper atom back on the surface. That is, the copper at infinity is placed back on the solid surface. After this, a vacant site is created in the interior and there will be electronic relaxation as well as elastic relaxations. And with these steps he estimated delta H1V for copper to be around 1.33 electron volt, which was close to the experimentally determined value of 1.28 electron volts. Right. So, the gist is, once the vacancy is created, there will be electronic and elastic relaxations in the region around the vacant lattice site. Now, let us try to develop an expression for the equilibrium vacancy concentration in a metal. So, let us denote it as X1V E. So, this denotes the equilibrium vacancy concentration. So, let us consider there are big N number of atoms and small m number of vacancies on total of n plus n lattice sites, and the Gibbs free energy change because of formation of n vacancies, as we have seen earlier, would be n times delta H1V minus T times n delta S1V vibrational minus T delta S1V configurational. And in order to get to the equilibrium number of vacancies, we need to differentiate with respect to small n, and where the derivative of delta G prime 1V with respect to small n is 0, that gives the equilibrium number of vacancies. Now, we first need to express this delta S1V configurational in terms of the number n, and that is easy to do. So, we can consider this as a mixture of big N number of atoms and small n number of vacancies, and the number of ways, let us denote it by omega, in which n atoms and n vacancies can be arranged on n plus n number of sides would be n plus n C n, and this can be written as n plus n factorial divided by n factorial times n factorial. And we know the delta S1V configurational would be given by the Boltzmann equation k ln omega. So, this should be equal to k ln n plus n factorial divided by n factorial times n factorial. Now, if we use Stirling's approximation, which states for large values of x, ln x factorial is equal to x ln x minus x, and both the numbers big N and small n are large numbers here. So, we can use Stirling's approximation. Before that, if we simplify this further, this will be k ln n plus n factorial minus k ln n factorial minus k ln n factorial. And if we apply Stirling's approximation to each of this logarithmic term, first about this factor x, here n plus n minus n will get cancelled. So, we will get delta S1V configurational as k n plus n ln n plus n minus n ln n minus n ln n. And if we rearrange the term, taking negative side outside, we will get delta S configurational 1V would be minus k n ln n over n plus n plus n ln n over n plus n. Now, both big N and small n are large numbers, but we should note that the small n is typically much lesser than this big N. The number of vacancies in a crystal are typically much less than the number of atoms present in the crystal at any temperature. And so, this n over n plus n is approximately equal to 1. So, we can get rid of this second term here. So, we get delta S1V configurational equal to minus k n ln x1V. This term here, small n over n plus n, is the side fraction of the vacancies. So, let us denote it as x1V. So, if we substitute back in our expression for delta G1V prime, we get delta G1V prime is equal to n delta H1V minus T times n delta S1V vibrational plus KT n ln x1V. And to get to the equilibrium vacancy concentration, we differentiate delta G1V prime with respect to n, and this should be equal to 0. So, if we differentiate the right hand side here with respect to n, we get delta H1V minus T delta S1V vibrational plus kT ln x1V, and in this case this is an equilibrium vacancy concentration. So, we should denote this more specifically as x1V E, the equilibrium vacancy concentration. And so, if we rearrange, we get the equilibrium vacancy concentration x1V E to be equal to exponential delta S1V vibrational by K times exponential minus delta H1V divided by KT. So, this is the expression for equilibrium vacancy concentration in terms of the enthalpy of formation of a monovacancy and the vibrational entropy change due to formation of a monovacancy. Now, the first term delta S1V vibrational is typically between 1 to 2 K, where K is the Boltzmann constant. So, this factor you will see will be typically between 2 to 5, and most of the time this is ignored, and the main reason for this is the factor of 2 to 5 typically comes within the experimental errors. When we determine the vacancy concentrations experimentally, the experimental errors involved are larger than this factor. So, typically you will see very often the first term is ignored and we write x1V E as exponential minus delta H1V by KT. Obviously, when we write delta H1V in terms of joule per atom, this constant in the denominator here is K, but if we express the enthalpy of vacancy formation in terms of joule per mole, this should be replaced appropriately by the gas constant R. So, we can see the equilibrium vacancy concentration increases exponentially with temperature, and near the melting point x1V typically is about 10 to power minus 4 side fractions. So, if we consider 1 mole of the crystal, there are roughly 10 to power 23 atoms, and so there will be around 10 to power 19 vacancies present in the crystal at equilibrium near the melting temperature. Now, there can be multiple vacancies formed on adjacent lattice sites. These are referred to as vacancy clusters. So, if there are 2 adjacent vacancies, it is denoted as divacancies. The 3 adjacent vacancies will form a trivacancy, and so on. Their concentration typically will be much smaller than the individual vacancies. However, the divacancies may become important. So, let us look into the energetics of divacancies. A divacancy is nothing but a pair of vacancies on adjacent atomic sites. So, if we consider through purely statistical point of view, that means if we ignore the binding energy between 2 adjacent vacancies, then the divacancy concentration or the number of divacancies, let us denote it as N2V, can be given as total number of pairs times the probability the given pair is a divacancy. So, N2V can be given as the first term here, the total number of pairs can be given as number of bonds per atom times the total number of lattice sites, which in this case would be N plus NV. NV is the number of individual vacancies, and since we are counting each bond twice this way, so we apply a factor of half. So, what is the probability that a given pair is a divacancy? That means the first selected lattice site is a vacancy and also the next selected site is a vacancy. So, the probability that a given site is a vacancy is its concentration x 1 v. So, this is simply x 1 v square, and so the fraction of divacancies x 2 v is given as half z x 1 v square. This is purely statistically, that is ignoring binding between vacancies. However, there will always be a binding energy associated with two adjacent vacancies, and it is easy to see why. Because to form the first vacancy, the z number of bonds have to be broken, but to form a vacancy on an adjacent lattice site, we need to break one less bond. So, this is a simple reason. Also, there will be other changes associated with the formation of second vacancies, and so there will be a binding energy associated with the formation of a second vacancy, and therefore, delta H 2 V, that is the enthalpy of formation of a divacancy, will always be less than delta H 1 V times 2. So, the enthalpy of formation of a divacancy is not same as enthalpy of formation of two monovacancies, and delta H 2 V is typically given by 2 delta H 1 V minus B 2, where B 2 indicates the binding energy of the divacancy. And so, x 2 V is given by z by 2 exponential minus delta H 2 V by k T, or x 2 V equal to z by 2 exponential B 2 by k T times exponential minus 2 delta H 1 V by k T, and exponential minus 2 delta H 1 V by k T is nothing but the square of x 1 V. This should be z by 2 exponential B 2 by k T times x 1 V square. Now, the question arises, if the enthalpy of formation of second vacancy is less than that for the formation of a individual mono vacancy, then why is the second vacancy not forming always adjacent to an existing vacancy? And the answer again lies in the compromise between enthalpy and entropy. Although the formation of second vacancy adjacent to an existing vacancy requires less enthalpy, but by doing this, by putting the second vacancy adjacent to an existing vacancy, we are also reducing the number of possible configuration in which the second vacancy can exist, and so it causes a reduction in entropy, and that is why the second vacancy will not always exist as a neighbor to an existing vacancy. In fact, the number of divacancies at equilibrium are typically much less than the number of mono vacancies. So, let us look into an example that I have plotted for platinum. So, here I have plotted the log of concentration of mono vacancies and die vacancies for platinum. The enthalpy parameters are for the platinum are the enthalpy of mono vacancy formation is about 1.32 electron volt, and for die vacancy the binding energy is about 0.19 electron volt, and so delta H2V simply equal to 2 delta H1V minus B2 would be about 2.45 electron volt. So, obviously, the magnitude of the slope of log x2V versus 1 by t should be larger than that for log x1V versus 1 by t. We can see at smaller temperatures or at larger values of 1 by t, the difference between x1V and x2V is much large, and the difference reduces as the temperature increases. So, if we consider two temperatures at 400 degree centigrade, the difference is about 9 order of magnitudes. As we go to 1760, which is very close to the melting point of platinum, the difference is about 3 orders of magnitude. So, the die vacancy concentration becomes significant, if at all, only at very high temperatures close to the melting temperature. So, typically at lower temperatures the die vacancies would not contribute much to the diffusion, although die vacancies can diffuse very fast. But these die vacancies do play important role in quenched alloys. For example, the age hardenable aluminum alloys during solutionizing are quenched from a very high temperature close to the melting temperature. Now, at high temperature there are large fraction of die vacancies, and because of the quenching those fractions of die vacancies are also retained at room temperature. Now, it is generally not desirable that the aging starts at room temperature, but because of these retained die vacancies, and since the die vacancies diffuse very fast, in many aluminum alloys the aging will start at room temperature. That is referred to as natural aging, and it is not desirable because the precipitates which are formed during natural aging do not give the best properties to the age hardened alloys. And so, the die vacancies at normal temperatures are not considerable, they do not contribute much to the diffusion, but at higher temperatures their fraction may become significant. We can apply similar treatment to higher vacancy clusters like tri vacancies and higher order clusters, and as we increase the number of vacancies their contribution or their fraction would keep decreasing. So, it is only sufficient to consider mono vacancies, which is very important, and in some cases the die vacancies. Okay. So, that is all for this lecture. Thank you.